Welcome back to the deep dive. Today, let's take a moment. I want you to really think about what thinking actually means.
hmm
And then try applying that concept to these cutting-edge AI models. Because, it looks incredibly impressive when a large language model explains its thought process, doesn't it?
It really does. It feels like you're watching actual intelligence unfold.
Exactly. But what if it's not quite what it seems? What if that visible thinking is, well, maybe an illusion?
That's the core question, isn't it? And that's precisely what we're going to dig into today. This deep dive is all about these large reasoning models, LRMs for short.
Right, the AIs that generate those detailed step-by-step thinking processes before they give you the final answer.
Exactly. And our mission here is to, look past the shiny demos and try to understand their fundamental capabilities. How do they really scale when problems get more complex?
And critically, what are their limitations, especially the surprising ones?
Right. And we're basing this on some solid research, not just guesswork.
Yeah, we're drawing from a pretty rigorous recent study by researchers at Apple. The title kind of gives it away. The Illusion of Thinking. Understanding the strengths and limitations of reasoning models via the lens of problem complexity.
It's a fantastic paper. Really gets under the hood.
So these LRMs, there's sort of a new evolution.
Yeah, you could say that. Recent generations of the big frontier models, think OpenAI's O1 or O3, DeepSeek R1, the Claude 3.7 Sonnet thinking model, Gemini thinking, they've introduced these specialized variants.
So they're not just the standard LLMs we've been hearing about for a while. These are specifically built differently.
Well, they're engineered specifically to produce these detailed internal reasoning steps. That's their defining feature.
That explicit thinking mechanism, like generating a really long chain of thought, sometimes they even seem to reflect on their own steps before spitting out the answer.
Exactly. CT, self-reflection, all that stuff. And look, on the surface, they've shown some really promising results on standard reasoning benchmarks.
Right, you see the scores. And some researchers are even suggesting, this is a big step towards artificial general intelligence, AGI.
The hype is definitely there. But the paper really highlights that despite these claims, we don't sufficiently understand their fundamental benefits and limitations yet.
How so? What's the problem with the current ways we test them?
Well, for one, current evaluations on things like math and coding benchmarks often suffer from data contamination.
Meaning the model might have already seen the answers or bits of them in its training data.
Precisely, which obviously skews the results. And maybe more importantly, these standard benchmarks don't really give you insight into the structure or the quality of the internal reasoning. You just get the final answer,
Yeah.
mostly.
Okay, that's a huge blind spot. If the test might be flawed and you can't clearly see the process, how can we possibly know if they're genuinely reasoning or just, I don't know, pattern matching really well?
Exactly. So if the standard benchmarks have these limitations,
Then you need a different approach to really peel back the layers, right? What did the researchers do?
that's where it gets clever. Their solution was to use these controlled puzzle environments. Think of them like logic games.
Puzzles. Okay, tell me more. How does that help?
Well, these puzzles allow for really precise manipulation of what they call compositional complexity. Basically, how many steps or interacting parts are involved.
So you can carefully turn up the difficulty.
Exactly.
Okay.
While keeping the underlying logical structure consistent. And crucially, this lets them analyze not just the final answers, but those internal reasoning traces the thoughts.
Okay, that makes sense. What kind of puzzles are we talking about?
Well, a classic one they used is the Tower of Hanoi. You know the one. 3 pegs and discs, move them all, following the rules.
Right, can't put a bigger disc on a smaller one. I remember that.
Yeah. And the key thing is the minimum number of moves required scales exponentially. It's 2 to the power of n minus 1.
Exponentially.
Wow.
So adding just one more disc makes the problem much harder in a very predictable way.
Precisely. That gives researchers incredibly precise control over the complexity knob.
Got it. Any other examples?
They also use checker jumping. It's a one-dimensional puzzle, red and blue checkers, empty space in the middle, and you have to swap them all.
Okay.
Its difficulty scales quadratically. The number of moves is n plus 1 squared minus 1. So another way to control complexity, but with a different scaling factor.
Interesting. Different scaling laws.
Right. And they mentioned others too, like river crossing puzzles, blocks world. The common thread is this ability to precisely control complexity and analyze the steps.
Okay, so they set up these controlled experiments.
Yeah.
Now, what did they actually find when they put these LRMs and standard LMMs through their paces?
This is where it gets really counterintuitive. They found three distinct performance regimes when comparing LRMs with their standard counterparts, even when giving both the same amount of computational resources.
3 regimes. Okay, lay them out for me.
Regime 1,
Yeah.
low complexity tasks. Here, surprisingly, the standard LLMs, the ones without the explicit thinking steps, often outperform the LRMs.
Wait, outperformed. The smarter reasoning models did worse on easy problems.
Yep. They showed greater efficiency and sometimes even better accuracy. It challenges that simple idea that more thinking is always better.
Huh. Why do you think that is? Is the thinking process itself adding noise or overhead on simple stuff?
That seems plausible. There's a computational cost to generating those long thought chains, right? Maybe for simple problems, that cost outweighs any benefit, or even, as you said, introduces errors or inefficiencies.
Okay, so that's regime 1. What about the middle ground?
Regime 2, medium complexity tasks. This is where the LRMs start to shine. Here, the additional thinking does provide an advantage.
Ah, so the gap widens.
Exactly. The performance gap between the thinking and non-thinking models grows. This is kind of the sweet spot where the LRM approach seems to live up to its promise.
Okay, makes sense. There's a point where the complexity warrants the extra steps. So what happens when you crank the difficulty way up? Regime 3.
Regime 3, high complexity tasks. And here's the kicker. Both types of models, the thinking LRMs and the standard LLMs, experience a complete performance collapse.
Complete collapse, like they just fail entirely.
Accuracy drops effectively to zero, regardless of their supposed thinking capabilities.
Wow.
The paper notes that LRMs might delay this collapse slightly compared to standard models, push the boundary just a tiny bit further, but ultimately, they hit the same wall.
So that built-in reasoning process doesn't fundamentally save them when things get really tough.
Doesn't seem to. They face the same fundamental limitation.
And it gets even weirder, right? Something about how much effort they put in.
Yes, this was another really puzzling finding. As the problem complexity increases and the models get closer to that accuracy collapse point.
You'd expect them to try harder, right? Generate more thoughts.
You would.
Right.
But counterintuitively, they start to reduce their reasoning effort. They actually generate fewer thinking tokens.
They generate less thought, even though the problem is harder.
Exactly. And this happens even when they have plenty of budget. Like they're allowed to generate many more tokens. They're nowhere near their output length limits.
So they have the capacity to think more, but they just don't?
Seems like it. It suggests some kind of fundamental scaling limitation in their reasoning capability relative to the problem's complexity. It's almost like they sort of give up internally before even using all the resources they have available.
That is genuinely strange, like an internal governor kicks in saying, nope, too hard, pulling back now. What does that tell us about what's actually happening inside those reasoning traces? Did the puzzles let them see that?
Yes, that's the beauty of the puzzle environments.
Yeah.
They could actually dig into those thoughts.
Choopy think.
Well, for the simpler problems back in Regime 1, they found LRMs often figure out the correct solution quite early in their thought process.
Okay, so they get the answer.
But then,
Yeah.
they often inefficiently continue exploring incorrect alternatives. They keep thinking, but about the wrong paths.
They call that overthinking, right?
It's exactly overthinking. It leads to wasted computation, makes them less efficient than the standard models that just gave the right answer and stopped.
So they find the needle, but then spend ages looking through the rest of the haystack anyway. What about when problems get harder in Regime 2?
As problems become moderately more complex, the pattern kind of reverses. Models tend to explore incorrect solutions first, and only later, sometimes deeper into their thought process, do they arrive at the correct one.
Okay, so the exploration seems more necessary there. And then in Regime 3, the high complexity.
Beyond a certain threshold, they found the models completely fail to find any correct solutions anywhere within their thought processes. It's not just the final answer that's wrong. The entire reasoning trace is flawed.
So it seems like they have some ability to explore and maybe self-correct at moderate levels, but it's limited.
It seems so. The analysis shows some self-correction capabilities, yes, but also these fundamental inefficiencies like overthinking and very clear scaling limitations. The whole process breaks down.
Okay, now let's get to what feels like the real core of the illusion idea. The finding about explicit algorithms. This one really blew my mind when I read the paper.
It's a truly eye-opening result. They tested what happens when you give the LRM the exact solution algorithm for a puzzle.
Like literally spelling out the steps. For something like Tower of Hanoi, you give it the recursive solution.
Exactly. Provide the explicit algorithm right there in the prompt.
Surely that must help.
Mm-hmm.
If you tell it exactly how to solve it.
That's what you'd think. But the LRM's performance did not improve.
Seriously, no improvement at all.
Nope. And the accuracy collapsed that point where performance drops to 0 still happened at roughly the same complexity level.
Okay, hold on. That's huge. It's not just that they struggle to figure out the solution.
It strongly suggests they struggle even to execute prescribed logical steps, and maybe even to verify their own reasoning against those steps.
So it raises fundamental questions about their ability to do symbolic manipulation, to actually follow logical rules consistently.
It really does.
Yeah.
It's less like reasoning and more like something else is going on.
Mhm.
Maybe sophisticated pattern matching that breaks down when forced into strict algorithmic execution.
Wow. Okay. And there was another major limitation too, wasn't there? Something about inconsistency.
Yes, another striking finding. The model showed wildly inconsistent reasoning abilities across different types of puzzles, even when those puzzles required a similar number of total moves or seemed, on the surface, to be of comparable logical difficulty.
Can you give an example?
Yeah, the paper points out the Claude 3.7 sonnet thinking model. For the Tower of Hanoi, it could actually perform quite well, generating up to 100 correct moves for N10 disks, which is pretty complex.
Okay, 100 correct steps is impressive.
But for a river crossing puzzle, a specific variant where N2 requires only 11 moves in total to solve.
So a much simpler puzzle in terms of total steps.
Right. But the same model could only produce about 4 correct moves before completely failing.
4 moves compared to 100. For a puzzle that only needs 11 in total, that's drastically inconsistent.
It is. And what does that suggest?
Well, it makes that earlier point about pattern matching seem more likely, doesn't it? Maybe it's seen lots of Tower of Hanoi examples online in its training data.
Exactly. Tower of Hanoi is quite common on the web. Programming examples, explanations.
But maybe complex river crossing puzzles are much rarer?
Plausibly, yes.
Yeah.
So the model might be relying on memorized patterns or strategies specific to Tower of Hanoi, rather than possessing true, generalizable reasoning skills that can apply flexibly across different logical structures.
It points to a fundamental limitation in transferring learning or strategy.
It certainly seems that way.
Okay, so let's try and wrap this up. Bringing it back to the core message for you, the listener, navigating this world full of AI. What are the key takeaways here?
Well, I think the main point is that despite these advanced thinking mechanisms, these displays of internal reasoning, current large reasoning models have some really fundamental limitations.
Yeah, they don't seem to generalize reliably beyond certain complexity thresholds. That collapse point is real.
Right. And their reasoning effort can paradoxically decline just when things get toughest. They can overthink simple problems, wasting resources.
And maybe the most damning findings, they struggle even to follow explicit algorithms given to them.
And show that striking inconsistency across different types of logical problems.
These insights, taken together, they really challenge the sort of prevailing assumptions about LRM capabilities, don't they?
They absolutely do. It suggests that our current approaches, building these ever larger models that generate thought chains, might be hitting some fundamental barriers. We might not be as close to truly generalizable reasoning as some of the hype suggests.
So, thinking about that illusion of thinking, how might you, our listener, reevaluate the reasoning you see from the AI tools you interact with every day, given these findings?
It prompts some deeper questions, right?
Definitely. Like, what does truly robust, generalizable artificial intelligence reasoning actually look like? If this isn't quite it, what are we aiming for? And maybe most importantly, how far are we really from achieving it?